Hello everyone, I welcome you to another video lesson. In today's lesson, we'll discuss queues with finite capacity. Not all queues have infinite capacity. For example, we'll not always face situations where the server is able to serve infinite number of people. Now, having an infinite capacity is possible when there is a server who issues tickets in a suburban transport system connecting various parts of the city. There is no limit to the number of customers who can be served through the train transport system, and in this case, the number of tickets issued per day need not be necessarily restricted. So we consider such queues as queues having infinite capacity. However, when there is a transport system connecting two cities, and when there is a reservation that needs to be made before you travel on the train connecting these two cities, there, the capacity will be finite. Or in the cases of cinema halls, in which the number of seats included in the cinema hall is always a finite number, and let's assume that a cinema hall has 100 seats, which can house 100 people watching a particular show at the cinema hall. If there are 105 people who wish to watch the movie, then the people who arrive, the last five people who arrive at the queue will have to look out for a different show time or a different cinema hall because of the finite capacity of the cinema hall. So these are examples of queues with finite capacity. And in today's video lesson, let's understand the various possible analysis which can be done for queues with finite capacity. We call these queues as an MM1 and FCFS model, where the two M's denote the Poisson process of arrival of the customers into the queue, and the second M denotes the service time, which follows an exponential distribution. In today's lesson, we'll look at a single server who's trying to serve the customers with a finite capacity of n, and this finite capacity is inclusive of the person who's being served and the people who are waiting in the queue. As a general assumption, let's assume that the discipline of the queue is on a first come, first served basis. We have the following formulae to be understood before we go into solving the problems. The probability that there are zero customers in the system is given by P naught is equal to 1 minus rho upon 1 minus rho to the power of n plus 1, where rho is the traffic intensity, which is the ratio of the number of arrivals to the number of departures in the system. And the probability that there are n customers in the system depends on whether rho is 1 or not 1. The average number of people in the system, denoted by LS, is denoted by these two different formulae, which depend on the value of rho. The average number of people in the queue will in fact depend on what is called as the effective arrival rate. The effective arrival rate is denoted by lambda dash, this is lambda times 1 minus Pn. By effective arrival rate, we denote the actual arrival rate which happens because of the finite capacity of the system. Because once the entire queue is occupied, we may lose customers, and that causes a dent in the arrival rate, which means lambda will be reduced to lambda dash. And this lambda dash is what we call as the lambda effective or the effective arrival rate. So to determine the average number of people in the queue, which is LQ, or the average waiting time of a customer in the system, which is WS, or the average waiting time of a customer in the queue, which is WQ, we take into account not only lambda, we take it as lambda dash. A barber shop has space to accommodate only 10 customers. He can serve only one person at a time. If a customer comes to the shop and finds it full, he goes to the next shop. Now, this tells us that we lose customers if the barber shop is already full. So lambda dash comes into effect. Customers randomly arrive following a Poisson process at an average rate of 10 customers per hour, and the service time is 5 minutes for a customer. And that follows the negative exponential distribution. We are asked to determine the probability that a customer will have to wait for his service and the average time spent by a customer waiting in the queue. From the question, we can observe that this is an MM1 10 FCFS model. The model here is MM1. The two M's denote the arrival and the service rates, which are Poisson process and the exponential distribution. And there is only one server because the problem tells that the barber can serve only one person at a time. And the shop has space only for 10 customers, so the capacity is finite and at 10. The arrival rate is 10 per hour, that's pretty straightforward. And the time taken to serve one customer is 5 minutes, so the time taken to serve 12 customers will be 60 minutes because we can just multiply both sides by 10, and that gives us the service rate, the rate of service as 12 per hour. Do not observe, it's good to observe that we have converted both arrival and service rates in terms of the same time unit per hour. So we find the traffic intensity, which is the ratio of lambda to mu at 5 by 6. The capacity of the system is at 10 customers, so n is 10. Now we are supposed to determine the probability that a customer will wait. Now a customer will wait and will not leave if at least one of the waiting spots is available. There's no one already in the queue, the customer need not wait and he gets served. The question wants us to find the probability that he waits. So he waits. If he waits, there is already one customer and there is also a waiting space available for this customer. So this implies the number of people in the barber shop is a number between 1 and 9, both inclusive. It is not 0 because if n is 0, he need not wait, he'll get served. And it's not 10 also because if it's 10, there is no place to sit and he'll leave the barber shop. So to determine this probability, it is enough if we subtract the value for P0 and P10 from 1. We know that the sum of all the probabilities will be 1. So from that sum, we can directly subtract P0 and P10. So we find P0 and P10 separately. P0 is the probability that there are 0 customers, that comes down to 0.193. The probability that there are 10 customers comes down to 0.0312. A customer will wait in the shop with the probability of 0.7758. The average time spent waiting in the queue, WQ, is the ratio of LQ to lambda dash. We need lambda dash for that, we need LQ for that, and LQ depends on LS. So we first calculate LS here. Using the formula we already stated, LS comes down to 3.29289, and lambda effective comes down to 20 times 1 minus P10. We already know P10 is 0.0312, so that comes down to 9.688. So we can observe that lambda dash is less than lambda because of the finite capacity of the queue. So LQ comes down to 2.481 and WQ comes down to 0.2561 of an hour, which is 15.36 minutes. The average waiting time for a customer in the queue is 15.36 minutes. The second problem, we have this situation. Assume that goods trains are coming in a yard at the rate of 30 trains per day following the Poisson process. And we suppose that the inter-arrival time follows an exponential distribution. The service time for each train is also exponential with an average of 36 minutes. The yard can admit 9 trains at a time. There are 10 lines and one is reserved. So there are only 9 trains at a time. This indicates the finite capacity. We are supposed to calculate the probability that the yard is empty, the average queue length. So we have an MM1 queue. The arrivals follow Poisson process and the service follows an exponential distribution, and there is only one server. Now the yard can admit 9 trains at a time, so the capacity of the queue is 9. So we have lambda 30 trains in one day. And since it is a yard, we consider a 24-hour time limit. And there are every train takes 36 minutes to get served. So for 10 trains, it will take 360 minutes. So for 10 trains, it will take 6 hours. And in 24 hours, we'll have 40 trains being served in the yard. So in a day, there are 30 trains arriving and 40 trains being served. So lambda is at 30 and mu is at 40. The traffic intensity, obviously, is the ratio of 30 to 40, which is 3 by 4. And the capacity of the yard is at 9. So the probability that the yard is empty is P naught. P naught comes down to 0.2649 using the formula we just used. The average queue length depends on LS and lambda dash. So we first find lambda dash, the effective arrival rate that comes down to lambda times 1 minus P root to the power of 9. 1 minus p to the power of 9. And p9 is p naught times rho to the power of 9, that is 0.019. So lambda dash, the effective arrival rate, is a touch shorter than the actual arrival rate is at 29.4. And then we need LS. So we find LS using the formula. Rho is at 3 by 4. And simplifying the other terms, we have LS at 2.40, which means LQ is at 1.665. So this gives us both answers. The average queue length is at 1.665 and the probability that the yard is empty is at 0.2649. The last problem. At a railway station, there's only one train handled at a time. The railway yard is sufficient only for two trains to wait while the other is given a signal to leave the station. So this once again hints at a finite capacity. Trains arrive at the station at an average rate of 6 per hour. The railway station can handle them on an average of 12 per hour. Assuming Poisson arrivals and exponential distribution, we are asked to determine the average waiting time of a new train arriving and the probability that the station is empty. So the Poisson process of arrival and the exponential distribution taken to serve a train hints that we have an system and only one train is handled at a time. So the number of servers is just one. The capacity of the queue is finite, since two trains can wait while one is served. So that's a 3. And we follow the FCFS model. So arrivals follow the Poisson process at 6 per hour, and the trains is served using the exponential distribution at 12 per hour. The number of servers is 1, the capacity is at 3. With all these data, we go into the solution. The traffic intensity is at 6 upon 12, which is at 0.5. The probability that the station is empty is P naught, which is 1 minus rho to the ratio of 1 minus rho to the power of n plus 1. That comes down to 0.533. And we need effective arrival rate. So we also calculate P3, the probability that the capacity of the system is reached. P3 is P naught times rho to the power of 3, that comes to 0.066. So to find WQ, we find LQ, and to find LQ, we need LS. We will find LS using the formula, using the values of rho and capital N, the capacity. We have LS at 0.733. So the effective arrival rate is not 6, it's a fraction short of 6. Is 6 times 1 minus 0.066. That comes down to 5.604. And LQ is found as LS minus lambda dash by mu. That comes down to 0.266. And WQ, the average time spent waiting is in the queue is LQ by lambda dash. That's 2.82 minutes as the ratio of LQ to lambda dash. And the average waiting time in the system is the ratio of LS to lambda dash. That comes down to 7.84 minutes. So in this video lesson, we understood the difference between queues with finite capacity and queues which are infinite capacity, which have an infinite capacity. And this caused a difference in the formula. We saw the two formulas are different as we have a change in the arrival rate. We calculate a new quantity known as the effective arrival rate, and that affects all the answers in every problem. Next, we look at a model in which there are more than one servers available with a finite capacity. We denote the model by the notation MMS and FCFS models, where the arrivals follow the Poisson process, the servers follow the exponential distribution, The number of servers is S, and the capacity of the system is restricted to the n value of n, and the discipline is on a first come first served basis. The various quantities which measure this model will depend on the values of S, rho, and N. We'll first start with P naught, the probability that there are zero customers in the system. This will depend on the value of rho. If rho is 1, we have a formula. If rho is not 1, we have another formula. Similarly, if we are required to find out the probability that there are n customers in the system, once again, there are two formulae available. One, if n is between 0 and s, the number of servers, and one, when n is greater than s, and then we have the usual four measures available: LQ, LS, WS, and WQ. LQ, the average number of people in the queue, will depend on quantities such as S, rho, P naught, and capital N. LS will be LQ plus lambda effective by mu. Determining lambda effective, we'll use the same formula, which is lambda by mu times 1 minus Pn. And for Ws and Wq, we'll use lambda effective with Ls and Lq respectively. We'll go to the first problem today. A small emergency ward in the hospital has three doctors to treat incoming patients. But due to the limitations, the waiting area can accommodate a maximum of seven patients, including those being treated. The patients arrive following a poison process at the rate of 6 per hour, and each doctor can treat patients at an average of 3 per hour, where the service time is exponentially distributed. Now, we are supposed to determine three answers: the probability that an arriving patient will be turned away, the expected number of patients in the system, and the average time spent by a patient at the system. Now, we can clearly identify that the arrivals follow the Poisson process. The arrivals follow the Poisson process, and the service follows the exponential distribution. There are three doctors, so there are three servers. The maximum capacity of the system is 7. So with this data, we can proceed forward and solve the problem. The arrivals are at 6 per hour, the service is at 3 per hour. So the traffic intensity rho is equal to lambda upon S mu, which is 2 by 3, and that will help us solve the problem. Now, to find the probability that an arriving patient will be turned away due to full capacity, we'll have to find out the probability that the full capacity is reached. That is, the number of customers in the system is exactly 7. So we need to find out P7, and for P7, we need P naught. We need P naught, the value of S, the value of rho, and the value of n being 7. So S is 3, the number of doctors, rho is 2 by 3, the traffic intensity. So S rho is 2. We can use them in the formula for P naught, and since rho is less than 1, we'll use the first formula. So we first complete finding the answer for P naught, substituting all the answers in the respective places. We simplify P naught to be 0.118. And this 0.118 is combined along with the other quantities to find P7. And P7 is the product of P naught with S rho to the power of n and S factorial and S power n minus S at the bottom. So this simplifies down to 0.031. So the probability that a customer is turned away is 0.031. And since we'll be requiring this later, I also find the value of the effective arrival rate lambda dash. Lambda dash is lambda times 1 minus P7, which is 5.8135, a fraction short of the actual arrival rate, which is 6. Now we go to the second question. This question was about finding the average number of people in the system, which is LS. And we know that to find LS, we need LQ. So we find LQ using this long formula, which depends on S, rho, P naught, and capital N. Substituting the numbers in the respective places, we see that LQ is 0.5088. And using the value of LQ, we can find LS. LS is LQ plus effective lambda by 3, which is 2.4466. The average time spent in the system by a customer is the ratio of LS to lambda dash. And using the numbers we just found out, LS was at 2.4466 and lambda dash was at 5.8135. So this reduces the waiting time to 0.42 of an hour. That's 25.25 minutes approximately. For the second problem, we'll look at a bank which has service counters which are 2 in number, and its lobby has room for a total of 5 customers, including those being served. When the system is full, the arriving customers are lost and they leave immediately. So customers arrive at the rate of 4 per hour,
according to a Poisson process. Service times at each counter are exponential with an average of 20 minutes. We are supposed to determine three answers: the effective arrival rate, the average number of customers in the queue, and the probability that a customer has to wait upon arrival. So, looking at the data given here, we can find out that the arrivals follow the Poisson process and the service is at an exponential distribution. There are two servers available and a capacity is restricted to five customers. So we have S at 2, capital N at 5, lambda at 4, and we have 20 minutes per customer, which means in 60 minutes we'll serve three customers. Therefore, in 1 hour, the service is 3. So using these, we'll find the effective arrival rate first. Effective arrival rate depends on Pn. Pn will be the probability that the system is full. Up to 5 customers are there in the system. But to find Pn, we need P naught. So we'll first find P naught. We'll use the values of S as 2, rho as 2 by 3, S rho as 4 by 3, and N as 5. Using them in the first part of the formula for P naught, we see that P naught is at 0.2235. So the chance that there are 0 customers in the system is 0.2235. And this answer is used to find out P5. P5 will thus be P naught times 1 by S factorial times S bar n minus S into S rho to the power of n. So we know what P naught is. S is at 2, N is at 5. So now that we know P5, we can find the effective arrival rate, which is lambda times 1 minus P5, and lambda is at 4, and P5 is at 0.0588. Therefore, the effective arrival rate lambda dash is 3.7645. Moving on to the second subdivision, we have the average number of customers in the queue, which means we just need to find out LQ. We'll use the same long formula that we used for the previous problem. We'll use the values of S, rho, P naught, and capital N. Simplifying them gives us the answer of LQ at 0.4857. That's the answer for the second part. For the third part, we are supposed to find the probability that an arriving customer will wait. Now, the customer will not wait if there are 0 customers, because if there are 0 customers, he directly gets his service. And because there are two servers, he'll also get served if there is only one customer. And if there are already 5 customers in the system, he'll have to come later and he'll leave immediately. So the number of customers cannot be 0 or 1 or 5 if the customer should wait, which means the number of customers can only be 2 or 3 or 4. So the probability that a customer who's arriving in the queue will wait is the sum of P2, P3, and P4. I repeat this again. If there are 0 customers, both servers are available, so he doesn't have to wait. If there is only one customer, one more server is still available, so he'll not wait. If there are 5 customers, 2 customers are already being served and 3 people are in waiting, so there is no space to wait, and so the customer will leave. So the customer will wait only if there are 2 or 3 or 4 customers. So to find P2, we'll use the formula for Pn. And because n is equal to s, the number of servers, we'll use the first part of the formula, 1 by 2 factorial times s rho to the power of 2 times P naught. Substituting the numbers, we see that P2 is 0.1986. And to find P3, we'll use the second part of the formula, which is 1 by s factorial times s to the power of n minus s and s rho to the power of n and P naught all in product. And since n is equal to 3, we have P3 at 0.1324. And since n is equal to 4, we have P4 at 0.0882. So since the required answer is the sum of P2, P3, and P4, the probability that a customer will have to wait in the queue is 0.4192. So that brings us to the end of this video lesson where we discussed queues with finite capacity. We have discussed two cases. One, when there is only one server in the queue, and two, when there are more than one servers available in the queue. In both cases, we have learned a lot of new different formulae and we have used them in the concepts to find the corresponding answers. I hope you found the lesson helpful. I'll follow this soon with another video lesson. Thanks for watching.